problem number 9 is the distinguish between the triple point and the freezing point of a pure substance. For more pure substance, which among these two is higher? So, what is triple point? Okay, so triple point is the temperature where solid, liquid and vapor these three phases are in equilibrium. And no other substance is present, because for pure substance no other substance is present. Whereas the freezing point is the temperature at which solid and liquid phases are present and they are in equilibrium with each other. Now, the next part is for more pure substances, which among these two is higher? For a pure substance, the freezing point is higher. They have a positive slope of a solid liquid equilibrium. In the phase diagram. Next, we move to problem number 10, which says a substance X has the triple point at 15 degrees Celsius and 0.5 atmospheric pressure. The melting point and boiling points are 25 degrees Celsius and 300 degrees Celsius. Draw the schematic phase diagram of X. So, this is a pure substance. So, we draw pressure versus temperature, pressure in atmosphere suppose, and temperature in degree Celsius. So, the phase diagram will look like this. So, this is the region where solid phase is present, this is the region where liquid phase is present, and this is the region where vapor phase is present. Okay. Now, the triple point at 15 degrees Celsius and 0.5 atmosphere. So, this is the point here where all three phases, means solid phase, liquid phase and vapor phase, all these three phases, they coexist, and the temperature corresponding to this point is 15 degrees Celsius and the pressure is 0.5 atmosphere. Next is the melting and boiling points are 25 degrees Celsius and 300 degrees Celsius. So, melting point means when solid and liquid, they are in equilibrium. So, if we consider normal melting point and normal boiling point, so if this is your 1 atmosphere pressure, so this is the normal melting point, this point, this is the melting point, this is 25 degrees Celsius, this is melting point. Triple point we usually call T3, and a normal boiling point. So, if we extend this line, then we get the normal boiling point 300 degrees Celsius. So, this is your boiling point. So, pressure increases in this direction and temperature increases in this direction. Next, we move to problem number 11. It says, consider the phase diagram of one component system. Calculate the degrees of freedom at point X and Y. Also, how many phases can exist along AC, BC and CD. So, this is pressure temperature diagram. You see y axis is pressure and x axis is temperature. So, X is the region where solid phase is present. Okay. So, number of components is, this is one component system. So, number of component C is 1 at point X, one phase present, right, because along these three curves we get two phases. These three curves means AC, BC and CD. Along these three curves we get any point along these three curves represent two phase system. Outside these three curves we get one phase system. So, this X is solid phase here, we consider solid phase here. This is one phase system. So, C is 1 and then P, so one phase is present means P is 1 here, and here T and P both are changing, both are not constant, both are changing here. So, F we know C minus P plus 2. So, number of component 1, number of phase 1 and plus 2. So, total degrees of freedom here at point X. So, number of degrees of freedom we call F is 2 at point X. Point now at point Y. So, Y is on the curve CD. Okay. So, at point Y, two phases are present, two phases coexist here. So, P is 2. So, again as I said, both temperature and pressures are changing here. So, number of degrees of freedom at point X at point Y is, we say F is C minus P plus 2, C is 1, one component system, phase is 2, so plus 2, so we get 1. So, number of degrees of freedom at point Y is 1, and the next part is also how many phases can coexist along AC, BC and CD. So, number of phases along AC, BC and CD will be 2, right, 2 phases. As I mentioned, so along any point on these curves like AC, BC and CD, we get 2 phase system. So, number of phases along AC, BC and CD curves will be 2. Next we move to problem number 12. It says draw the phase diagram of for the iodine system. Triple point is 112 degrees Celsius and 0.12 atmosphere. Critical point is 510 degrees Celsius and 116 atmosphere. Normal boiling point, normal melting point is 114 degrees Celsius and normal boiling point is 185 degrees Celsius. Also, density of solid is greater than density of liquid. It is just opposite of water. In case of water, usually density of liquid is higher than density of liquid water is higher than density of ice. So we get here the positive slope for solid liquid coexistence line. Okay. So if we draw PT diagram, this is one component system. So we draw PT diagram here, pressure temperature diagram. So pressure here along y axis, pressure and then temperature along x axis. Okay. So the schematic phase diagram will be like this, and then you get this, and then you get this. So for water, if you remember, for water, these two lines, so these two lines, okay, so for water it will be like this. So this is for water. This is solid liquid coexistence line, right? So if we level them, so this is suppose A, this is point O, and this is okay point B, and this is C. So AC, AO is, so this side we have solid phase, solid iodine. This is a liquid phase, and this is your vapor phase. This is region. Okay. So AO means we have solid vapor coexistence line. Similarly, OB is liquid vapor coexistence line. And OC represents solid liquid coexistence line. Since density of solid is greater than density of liquid, so we get the positive slope of this line. So this is for this line we get the positive slope here. Okay. So this is positive slope. Slope is positive as rho solid is greater than rho liquid. So, and then for water we get this is negative slope, if you remember. Okay, so this one for water, and these three lines OA, OC and OB are for iodine. Okay. Now O is the triple point, but because at point O you get both, you get all three phases, right? Solid, liquid and vapor. So O is the triple point. The triple point. Okay, so at triple point, the temperature is 112 degrees Celsius and 0.12 atmosphere. So the temperature here is 112 degrees Celsius, and pressure here at the triple point is 0.12 atmosphere. Okay, next is normal boiling point and normal melting point. So normal melting point is 114 degrees Celsius. So if we consider this point is 1 atmosphere, Normal means normal boiling point and normal freezing point, we consider 1 atmospheric pressure, because as we change the pressure, freezing point, boiling point both changes, both these two things, both this term they change actually, both the values will change. So this is 1 atmosphere pressure. Now if we draw a line, horizontal line like this, so it meets it here, right? So this will be, since OC is the solid liquid coexistence line, so point C will be our normal boiling, normal melting point. This is 114 degrees Celsius. Now if we extend this line like this, okay, so now what we do, so we extend this line, suppose, okay, and this line also we will extend. Okay, now we want to check the normal boiling point, right? So normal boiling point, so 1 atmospheric pressure, so this OB, this curve is liquid vapor coexistence line. So if we extend this line up to this part, so here we get normal boiling point. This is 185 degrees Celsius. So this is melting point and this is boiling point. Normal melting point, normal boiling point. Then we need to also draw critical point, is 510 degrees Celsius and 116 atmosphere. So if we draw it like this, okay, so we get basically, we get here some point here, okay, so here we get this one. So this is your triple point, critical point. This is critical temperature Tc and this is critical pressure Tp, okay, sorry, Pc, critical pressure Pc here and critical temperature Tc. The value of Tc here is, this is the critical point, this is the critical point. So value of Tc here is 510 degrees Celsius and value of Pc here is 116 atmosphere. So this is the phase diagram of iodine. Now problem number 14 is, consider the one component system, indicate the relative magnitude of the specific entropies and the molar volume of phases in the neighborhood of point A, which is the 1, 2, 3 tipple point. Okay, so this is phase 1, this is phase 2 here, and then we have the phase 3 here. Okay, so it is evident that region region 1 is solid phase, right? So this is solid phase, this is liquid phase, and region 3 is vapor phase. Region 2 is liquid phase and region 3 is vapor phase. The entropies and the molar volume of the vapor phase is the highest, right? Because molar volume of usually in general, except water, in general, molar volume of or molar, first molar volume we consider. Molar volume of gas phase or vapor phase, it is greater than molar volume of Vmg if we consider molar volume of gas phase. So, Vml is the molar volume of the liquid phase and Vms is the molar volume of the solid phase. So, in general molar volume of the gas phase is greater than molar volume of the liquid phase, which is greater than molar volume of the solid phase in general. For water this is different, for water it is reverse, for water it is reverse. Okay. Water for that region we get negative slope in the PT diagram for water, for solid liquid coexistence line. Now, in general this is the case, and always molar entropy of gas is greater than molar entropy of liquid So, if we say molar volume of the gas is Sgm, molar volume of liquid is Slm, and molar volume of solid is Sm, then this here M stands for molar. Okay, so molar volume of gas is always greater than molar volume of liquid, which is greater than molar volume of solid, is always. That's why we get this kind of plots here. Okay, anyway, so now okay, so why it is like that? Because for gas we get entropy is very high, because particles are far apart, so they have more space, so more randomness here for gas phase compared to liquid phase. Liquid phase space is reduced, but for solid there is very less space, or there is no space between the molecules to move around. So randomness increases in this direction. Okay, randomness increases, and we know randomness is the measure of entropy. So we get Sgm is greater than Slm is greater than Ssm. So the entropies and the molar volume of the vapor phase is the highest, right, as we see. Now the entropies, the entropy of liquid phase is higher than that of the vapor phase, that of the solid phase. And since we get positive slope of solid liquid coexistence lines, this is positive slope. As P increases, T also increases, or as T increases, P also increases. Okay. So that's how we get dp dt positive. Okay, positive slope means dp dt positive here. Since dp dt positive here, so since dp dt for solid liquid coexistence line SL is positive, greater than 0, and Vgm is always greater than Vlm. So the increasing order or decreasing order of molar volume molar volumes is Vgm is greater than Vlm is greater than Vsm, and for entropy it is Sgm is greater than Slm is greater than Ssm. Next we move to problem number 14. It says A substance exists in two solid modifications, alpha and beta, and also a vapor and a liquid. At a pressure of 1 atmosphere, alpha melts at a lower temperature than beta, which melts at a higher temperature to form the liquid. Also, alpha is denser than the liquid and beta is less dense than the liquid. Sketch the pressure temperature phase diagram, also show the triple point. So it's very similar to phase diagram of sulfur. So if we plot P versus T diagram, here P in atmosphere suppose and T in degree Celsius here. So pressure increases in this direction, temperature increases in this direction. So if we draw the phase diagram, it will look like this. So here you have the alpha phase, because at pressure 1 atmosphere, alpha phase melts at a lower temperature than the beta phase. So this is the beta phase, suppose. Okay. So this is this line. Okay. So we will discuss this one later. So this is suppose point C, and this is liquid region, this is vapor region, and this is point A, this is point B, this is D, and this is E. So this is suppose 1 atmospheric pressure. Okay, so this is 1 atmospheric pressure. Now AB, this line or this curve correspond to here alpha phase is in equilibrium with vapor phase, right? Alpha phase is AB corresponds to alpha phase is in equilibrium with vapor phase. So this is like this, and then BC represents beta phase. BC represents beta phase is in equilibrium with vapor phase. CE is liquid phase in equilibrium with vapor phase. Then BD. Now if we consider BD, in BD alpha phase here and beta phase here, so alpha and beta they are in equilibrium, okay, along line BD. So BD represents alpha is in equilibrium with beta. Next CD, if we consider CD, so beta phase is in equilibrium with liquid. So beta phase is in equilibrium with liquid. Now we have critical point. Okay, what is the critical point? So critical point here is E. E is the critical point. So this is the critical point. So E represents critical point. Critical point. So this is the corresponding pressure, because beyond this point we cannot distinguish between liquid phase and vapor phase, right? So this is critical pressure PC and this is critical temperature TC. So E is the critical point. Now how many triple points are there? Okay, triple points means 3 phases they coexist, right? So B at point B, if you see, so B is a triple point, right? So now triple points. How many triple points are there? Let's see. B is one triple point where alpha, beta and vapor, these 3 phases are there. right. D is another triple point where alpha, beta and liquid phases, right. Now C is another triple point here. At point C we have beta, liquid and vapor phase. Right. So, these are the triple points we get here. Okay. So, critical point is E, as I mentioned, this is the critical point, and then we have 3 triple points here, B, D and C. Next we move to problem number 15. It says the degrees of freedom at the triple point in the unary diagram for water. Okay. So, it is the phase diagram of water. Okay. So, consider phase diagram of water. So, degrees of freedom at the triple point. So, for water, for pure water, number of components C is 1, number of phases at triple point, if we consider P is the number of phases is 3. So, F is number of degrees of freedom F is C minus P plus 2. So, we get C minus 3 plus 2, so you get 0. So, at triple point there is no degrees of freedom, is 0. Next we move to problem number 16. It says a liquid phase produces 2 solid phases during dash reaction upon cooling, eutectoid, periseptic or peritectoid. Okay. A liquid produces, we already discussed this one. So, a liquid phase produces 2 solid phases during eutectic reaction. Upon cooling. So, this we already discussed when we discussed solid phase diagram. Next, move to problem number